this presentation is prepared by Sadaf Alam, but she's had to go to a conference, so I'm going to present it on her behalf with a few extra slides and so on to bring things down a little bit more to my level in areas where I'm using more simple benchmarks a few times so that I understand things a bit better. So we're looking at planning and designing of these hybrid applications on hierarchical platforms. We want to look at some of the performance and scaling bottlenecks. We've already seen some of these. It's quite difficult to see, isn't it? Yes, exactly. I'm going to go back and try that again because it seemed to fade into the darkness. Which so if you're quick, you can actually see what we're looking at here. Okay. And then tuning and optimization on our target platforms. So just to look at the hybrid programming. So just to reiterate what we're actually looking at here, we're looking at actually large-scale MPP systems. Okay, we're looking at that because it's the business of CSCS at the moment, at the current time, to look at MPP systems because these are the systems that are largest that are around. Okay, in the past, CSCS may have been vector systems or whatever. We're trying to get the best that's available at the time. Large-scale MPP systems, they're many core. We've said already they're going to be multi-socket and multi-core. So there are issues to do with non-uniform memory access and affinity that you need to take account of. We've got MPI between nodes and OpenMP on nodes. MPI between sockets maybe and OpenMP on sockets, which is actually more realistic, or even going further down onto even little dies that we said before about this manu-core processor. We don't even necessarily want to use all 12 cores for OpenMP because we have that extra NUMA effect. And on collections of cores and thread groups. So there are fixed bindings and affinities. These things are static. Just one thing, didn't actually say before, but just when we're talking about NUMA nodes, if you want to use a standard Linux command to find out about what the NUMA characteristics of your node is. If you want to do that on Palu, immediately you've done the salloc, of course, as Tim says, get off, because otherwise nobody can use the system. But if you salloc one node, then do an apron minus n1 NUMA control minus hardware. This will be on a compute node, and it will say, what are the NUMA characteristics of my hardware? If you do this on a machine that was like Rosa, you don't use salloc, you'd use a slightly different system with the Q-sub batch system, and do the same thing. Just tell me what the hardware is, you'd see something different. So here it's saying I've got 4 nodes on one node, right? From one core on one node, what do I see as the hardware of my node? It says I've got 4 nodes, NUMA-wise, and each one has 6 CPUs, and each one has 8 gigabytes of memory. Okay, so it's a 32 gigabyte node, 24 cores, but what it's saying is if I really want to separate this down into things that are important for non-uniform memory access, for where the performance hit's going to be, is actually, you should think of it as 4 separate nodes. What it's then saying down at the bottom, the node distances, and sometimes these aren't quite accurate, but they're reasonable, is that to go from one node to itself has a certain latency, a certain bandwidth, and so on. The lower the number, the better. And it's saying the diagonal is saying basically to go from here to itself is of a certain bandwidth or latency. To go to any other node is saying it's the same distance. If you've got to get off of your little NUMA node, from node 0 to any one of these 3, it's going to cost you pretty much the same. It doesn't matter. And that's the way the node's designed. On another system, you may find that is not as uniform. Okay, so that's just something to bear in mind. Whenever you go to a new system, this is not a Cray-specific thing, NUMA control. That's a Linux thing. So you go to any system, you can find that out. Okay? So on the Cray XT5, what do we actually have? We have 12 cores arranged on 2 sockets, 16 gigabytes of memory. This is a standard Cray designed marketing tool for showing what a compute node looks like. and where all the bandwidth impacts are. On the machine you've been looking at instead, Palu, Cray XE6, becomes a little different. We don't actually have one of the marketing slides. I think Roberta's got one. And so now we have, very similar to the previous slide, now it's 32 gigabytes of memory, got 2 sockets, but now we've got this NUMA affinity effect that we have to take into account on a socket. And so using that NUMA control, we can actually see what we've got. We've also got a very small 2-node Xeon-based cluster. And here we're mentioning this because you actually have an extra effect that you have to take into account beyond what we've talked about so far. So an AMD Opteron is a single hardware thread. But Xeon-based systems, power-based systems, if you get access to an IBM machine and so on, have an extra effect, and that's hyper-threading, or as it's now referred, pretty much universally, it's SMT, symmetric multi-threading. If you go on to the machine Julia, which is a Xeon-based cluster here, it consists of 2 sockets. Each one has 6 cores. But if you look at it through another Unix command, if you just cat /proc/CPU info, that tells you how many processors you've got. It doesn't tell you you've got 12, it tells you you have 24. Because for each one of those hardware threads, it pretends to the outside world it's an actual core. So you have to be aware of this extra effect when mapping things onto processors, and that is an extra effect you need to take into account with affinity. So on this particular slide, they've been shown with little dotted lines around the outside, because they're not real cores. Just to reiterate as well, because it always comes in important when you're designing your OpenMP code, that Amdahl's law is the limiting factor. Okay, so just to say you can't get away from this, if you start to parallelize your code with OpenMP, you must finish parallelizing it at some point. You can do it incrementally to check the results, but if you don't end up parallelizing almost all of it, you will be hit by Amdahl's law. And the efficiency you get at any particular point is given by the speed up over the resources. To give you an example of Amdahl's law, I hope you've all seen similar slides in many presentations before, but if you haven't, this is what we're talking about. Number of cores per node. If you parallelize 95% of your code, which is quite a lot, then on 24 cores, you'll still be limited to a speed up of probably about 12. Okay, don't expect that you get 100% speed up. If you don't, that's 95% is a lot of your code to actually go through and make sure it's all running in parallel and perfect efficiency. If you get anything lower, if you're only doing 20%, you're not going to get very much at all out of this. Okay, and even doing up to 80%, you're pretty much effectively limited to only getting a 4 times speed up on 24 cores, because the serial time now is the most important thing. It's just blocking you. So by all means do incremental parallelization using OpenMP to get the right result, but make sure you finish the job. Okay? And so here's the efficiency, the same curve but showing the efficiency, and we drop down as we go forward because that little bit of Amdahl's law on the formula, these bits, the S comes to be the dominant factor. We have that big, sorry, the 1 minus P bit is the dominant factor. It's the bit we haven't parallelized. Okay, and that's assuming you've parallelized it perfectly. So very important, make sure you finish the job, otherwise you'll come back and say, well, that OpenMP was no good to me at all, it produced a slowdown. And this is also the reason why we say as well that for OpenMP, in addition to your MPI, you should be thinking about being able to push further along the scaling curve rather than getting a faster speed up than your MPI if your MPI is already well parallelized. Because you've got to put a lot of effort in to the OpenMP to match the same thing. It's just you may be able to get a faster time to solution by using more processors. So the key attributes that you have to consider now as we move forward, more and more cores, and those cores now start to appear on sockets, on NUMA nodes. but it's more and more cores will be the future. The vector units that we mentioned before, we talked about this, these SIMD instructions, and these are getting fatter and fatter. Okay, so said if you don't get good usage out of those SSE instructions, AVX instructions, AltiVex instructions on these processors, you're getting a half or a quarter of your peak performance. And we have to look at hardware-assisted threading, hyper-threading. So at the moment, as I said, the Opterons don't have this, and they're not going to have it. It's not on the roadmap for AMD, but they're going to get something similar, which is 2 cores will start to share resources. They will be physically different cores, but they'll be starting to share the resources so that 1 out of 2 could grab all of the floating point if the other one doesn't need it. And this is a very similar idea. It's just AMD's way of saying we think this is a better approach than Intel and everyone else's. And we use multi-threading for a variety of these reasons. For latency hiding, that's why hardware threading is there. Get out of the way if you're blocked on something like I/O or memory accessing. Task parallelism. We want to get some better dynamic load balancing, and there are certain decomposition limits of MPI which we can improve. For example, if you've parallelized something only in 2 dimensions of a 3-dimensional problem, OpenMP may be the easier way to get some parallelism in the 3rd dimension. So, we'll now look at some scaling and so on bottlenecks. Just having a quick look at some experiments carried out on an XT5, XE6 and InfiniBand cluster. On these machines we have a variety of different compilers. This is very important. Do try out a variety of compilers. You may find very interesting results from one compiler to the next. You can find, for example, as 2 of us were just discussing earlier, you go from PGI to GNU or PGI to Intel. PGI actually can have some quite poor effects depending on how you actually want to use your threads, particularly if you use them just to try and get multiple work going on the same core. But try out the different compilers. We've got on different machines some different vendor libraries for MPI, and we have the appropriate tools to see where the bottlenecks occur. And you should find that the results and the analysis should be reproducible on systems of similar configurations. So just to look at a quick couple of benchmarks now. SADAF likes to use the NAS parallel benchmarks. They are a very good set of benchmarks, but they're a little bigger than some of the things that you want to put on a slide. So I've gone, in a moment, I'm going to go back to a good old favorite of matrix multiplication, because we all can fit that on a slide to actually do some analysis. But looking at MPI-only kernels, some OpenMP kernels, and some combinations of the pair. So our target systems, you've already seen these. So we've got Rosa, the XT5, we've got Palu, the machine you've been working on, and we've got a Xeon cluster. So using the conjugate gradient NAS parallel benchmark, comparing on different numbers of cores using an OpenMP and an MPI version. What we can see here, using the vendor MPI, using the best MPI available, is a variety of different benchmarks with MPI and OpenMP being of similar performance all the way down. In this particular case, it looks as though OpenMP is slightly faster. And when we push out to the extreme, we get these numbers, but notice that we're looking at different numbers of threads in this case. Some code modifications that you might wish to actually also carry out in order to get better improvement out of these benchmarks. The first one is a serial case. This is clearly a reduction. So we use a reduction over here. There's some slight changes in the use of the variables here. Here we do a reduction, an MPI reduction's quite simple. You just do the thing serially, and then you use an MPI reduce to actually get your reduction variable. And that's how we manage to get different performances and slightly better on the OpenMP. The fast Fourier transform kernel, OpenMP in this case can be much faster than the MPI version. There's a lot of communication starts to go on the, in order to get transfer of data from one MPI process to the next. But in this particular case, OpenMP can just see the memory, and because there's so much communication, OpenMP can do a much better job than MPI. So this is where you have to think about your algorithm, whether your algorithm also matches well to OpenMP or MPI. If it matches well to MPI, it will be fine on OpenMP, but it's not necessarily always the same the other way around. And here again, there were some changes made to the MPI version to get onto the OpenMP version that in order to eliminate some of the requirements for memory transfers systems. Another point that's often made is what's the overhead of using OpenMP compared to just a serial version. So here's an example where you do an OpenMP version of conjugate gradient and of the FFT that's in those panel of benchmarks, and then just run it with one thread and see what the actual overhead of actually putting any of this in the first place is. This may not actually involve thread creation. It may just be what have I actually had to do calculation of do I have to even have a threaded region at all. And the overhead here is of the order of 1 or 2% at maximum. And using MPI, similarly, there was very little noticeable overhead in this particular case for using single funneled serial multiple. But that also depends on what your algorithm is, how much communication characteristics there are. Another aspect is the number of zones for a problem size. It may be limited how you do your distribution and how many MPI tasks you can have, and then you may be able to vary the number of threads. One problem with doing OpenMP should also be aware of is the compiler doesn't know when you actually give an OpenMP region how many threads you intend to use. So it can't optimize things around those number of threads. If it did have that information, then it may be able to do a much better job in terms of actually splitting up your loops. That's unfortunate, but the standard just says you must produce a code that can run on any number of threads. One other thing to think about is that distribution. So if you've got different numbers of possibilities for MPI and OpenMP, if you've got 24 tasks, for example, how many should you make MPI, how many should you make OpenMP, even on a node? Okay, specifically just looking at one node rather than going onto an interconnect. So here's an example of running another one of these benchmarks, the LU benchmark, and looking at the 24 cores that we have available on one of these nodes and what's the best way to use them. So here's some example from MPI tasks. The best two numbers are down here, using all 24 cores, which is nice. But there's a difference you can see in the numbers depending on how many threads you have and how many MPI processes you have. So the best number comes from having 4 MPI tasks and 6 OpenMP threads. And if you think about our NUMA characteristics, that's exactly what we would expect if NUMA was a significant factor here, because that's giving one MPI process out to each of the NUMA nodes and putting 6 threads on each of those NUMA nodes. Whereas the other one, the threads are then starting to actually try and do some work in this LU decomposition routine across NUMA nodes, even if it's in the same socket. So again, these are the systems we're looking at. The first two systems don't have anything to do with hyperthreading, but there's still all the NUMA effects that are required. Here's where we also mentioned about the fact that you should check the compilers. So there's a variety of different numbers using OpenMP, how many threads we have, as to what the performance of the compilers would give you. Notice in some cases that you might end up with some superlinear scaling. That can be an effect of the compiler. But if you also notice that the way you were getting those extra little effects, it wasn't as good as the Cray compiler could do anyway. And the Cray compiler doesn't show the same effect because it's doing a much better job anyway in its initial optimizations. But if you come along with a particular application, please try a variety of compilers. We now have 5 compilers available on the Cray systems. Okay, if you've got an extremely large application and it takes a long time to compile, just try it the once. Don't try and play around with too many compiler flags. But this can be quite significant. So we have PGI, Pascal, Cray, Intel, and GNU now.
By the way, do you know if there is any framework where you can test the different, or which helps to test the different compilers? Like you could provide the compiler commands and then different options you want to test, and then if we look at all the combination of the commands and compare it to, then you provide some routine to
across different compilers, not really, no. It's just a case of going in pretty much with your makefile and changing makefiles. Individual compilers, such as Pascal, do provide tools to generate lists of different compiler options. I can't exactly remember what the command's called. Pathopt. And that will then say, okay, right, here's a variety of these things. And then you can just run through. It's like an auto-tuning approach. Yep. Tests that we've tried out, or particularly Jean-Guillaume at the back has tried out a few times, actually you end up with once you've got the main options, but a number of things he tried, we're talking 1 or 2% differences, I guess. It was very, very minor differences some of those things will produce. And some of the things that are better you can guess anyway. But across compilers, no. Generally, it's a case of produce a different makefile, try it out, as things stand. But in this particular case, we're talking about a third faster from one compiler to the next. So a breakdown of runtime between the two compilers. Just made the name of the routine a little shorter over here so it fits better on the slide. But the compilation of the Cray here was able to get this routine much better compiled on the conjugate gradient example than PGI was doing. And this is from output from CrayPat. So you've been using CrayPat, I believe, yes? You've all been doing some nice exercises. So as I said, try out the different compilers and see what's going on. And we want to know what actually is going on. That was the same code. There were similar compiler flags. We're trying optimizations, 03 for Cray, 03 FastSSE for PGI. We're using the same tool, so what has gone different? So now I'm going to fall back into something that I understand a little better. It's easier to fit on the slides as well, and that's our good old favorite, doing something with matmul. So in this example, there's some allocation routines and so on. What I'm showing here is a matrix multiply using dgem. Okay, so this isn't in the slides there. We can get you a hard copy or put them online later. This is a call to dgem, the standard BLAS routine. Vendor optimized, as good as you're going to get doing your matrix multiplication. You're not going to match that by doing something with a triple nested do loop, even if you manage to do something quite clever with cache blocking. And then we also do a matmul. We've just expanded this out into how we would write it in Fortran, could be C, using a triple nested loop. The compiler, it doesn't matter really what order we put those loops in, the compiler at that level of optimization will know if we've done a good job or not and will reorder them for us. And it will do cache blocking for us if it's required. So I'm using -03 FastSSE, -03, and I've added these extra options. These are listing options. They say, actually tell me what you've done as a compiler. Don't just give me the executable back. Give me that little bit of extra information. I'm not going to go into what PGI does because it doesn't do anything exciting. But we'll have a look at what Cray does because it does something that's a little clever. So the timings for this matmul example, PGI had a dgem of 2.05 seconds. Nice, fast example. The matrix multiplication, 12 seconds. On Cray, we get a dgem result of 2.05 seconds. Actually, the matmul here is faster than the dgem, but it's minimal. Okay, it's about the same. These things, it's just a matter of maybe something was already in cache anyway, etc., etc. It could be helped by some effects, but that's a big difference. Okay, you agree? This is real code. So the Cray compiler is 6 times faster. So what we want to do is look at that listing to see what it did. So this is the listing of the .lst file that you get by putting that -RA flag on. And it's got some, it will give you your code back, and then it will say at the left-hand side some things that it's done. Okay? As I said, these aren't in the notes in front of you. This is something we can put online or whatever later for you to see. So there is a listing of these things in the notes. This is actually what the compiler listing will be telling you it's done. You can see how it modified things in primary loop types. So over here, just as an example of how it initialized the arrays, it said it could vectorize this sine and cosine. Okay, so it didn't actually leave sine and cosine as individual routines to be called. It said I can vectorize this loop, and I've got a better version of sine and cosine that I can throw a lot of data at once. It did some partial unrolling of the loop 4 times. It said I'll do 4 at a time here. That's where my vectorization level comes in. But the bit we're interested in is down here, is this mapmul. And what it's done is this A, it's saying it's found that this is a pattern that's quite common. So it's matched this pattern, and it's going to do something with that. And it's going to do it for not only for the outer loop, but everything inside. That's why it's saying it's second and third level of the loops. It's doing a pattern match. Okay, it pattern matched that triple do loop. That's part of the LST file. You can then look further down and get the actual message about, at that line, what did you actually do? And what it said is a loop starting at line 60, so it's really talking about the inner loop, but it's talking about the nest, was replaced by a library call. Okay, so it saw the pattern, I can do something with a library call there. And so what it actually did was it replaced it with the same dgem call that we're using in the other routine anyway. Okay, this is a trick in some way, but it's a trick because it's Cray compiler. It knows you've got a dgem library available because you're on a Cray machine, so it's therefore given you the dgem routine. And it will do this for several pattern matches. And this is something that Cray are always trying to get better pattern matches. Try and do things that it knows it can do better than you can. And that's why, even though it looked as though it was faster, that was just a little effect. It was doing the same thing. Yeah?
Your slide on the right at the top.
Yeah?
From where does it come?
From that comes from the .lst file as well.
Okay.
The listing file is very comprehensive. It begins by telling you what you compiled with, or what it actually interpreted your compilation as, which we'll see in a second. It then actually just lists this for you, so you don't need to go and find it anywhere else. And then it lists your code. It lists what transformations it's done, whether they're scalar, whether they're vector, and it also lists the variables, where they were used, etc. It's quite a nice feature. Other compilers will generate other information for you. Pascal will generate information. PGI will generate information. It just outputs it to standard error. And you will see, oh, I did something on this loop. In this particular case, PGI says, oh, I saw this was a nice pattern for vectorizing. Which it is. But Cray knows it's better for pattern matching. So that conjugate gradient example that we saw earlier, you'd get that output from it. It also saw a pattern match that it could do a less sophisticated one, and it could vectorize within this particular call, which was inlining. So that's why we got this much better speed up, 133 seconds rather than 194 seconds with the earlier example. And what that 03 translated to, you can also get, and this comes out of your listing file, and it will say it did all these things. Importantly, it gave very high levels of vectorization and scalar optimizations. Another thing that it did with FP2 is it said it didn't care too much about the accuracy of the results. It didn't stick too much to rounding and so on errors, which for some people, Oliver, we have, the community around the optimizer says, no, we need you to get that down as low as possible, and that inhibits some optimizations. You don't need to compile the entire application to generate this listing. You just need to compile your particular source code. So it could be one file out of a huge, great file. You just get the listing file. Now, we've mentioned all this about what a compiler will do. We're mentioning this from the point of view of MPI OpenMP for a reason I mentioned yesterday. And that is, if by just putting OpenMP in there, you may actually stop the compiler from doing its job. In this particular case, we've got the same code, apart from I put in just this OpenMP parallel do, some shared and private variables, on that area, on that block. How does that affect what the compiler can do in terms of its optimizations? Well, the cray timings for one OpenMP thread, so we're not trying to speed things up with 2 and 4, we're just trying to see what this version does against the serial version. DGEM is 205, that's what we expect, but the map pool loop has now gone out to 9.7 seconds. Still better than PGI, but it's not doing the 2-second thing anymore. Okay, that's much slower. So by telling the compiler to optimize on a specific loop, we've actually, in this case, prevented the compiler from doing a pattern match. Okay. So you have to go through and check your compiler listing. The other thing, if it was less sophisticated, that we could do to stop the compiler from doing its job of optimizing is, even on a more simple compiler, the compiler may look at this loop and say, well, actually, I think you've ordered it in the wrong way. It may be that you're going through on a really large stride pattern, whereas it can reorder these things to get a much better cache utilization, to stream through cache better. If you then go in and put your OpenMP parallel do loop on the outside of those, and it had been in the wrong order, again, you tell the compiler, you can't do anything. You're not allowed to move this loop around. So it's very important to go through and actually have a look at compiler listings and see what it's done. And if it says at some point that it's done reorderings and so on, you have to go in and manually change your code first so that you still allow the compiler to do its job later on. Okay. The other thing is mapping and control of those tasks and threads. So we have, for app run, N to say the number of tasks, S can say the tasks per socket. Actually, that's not what it is. Minus capital S is saying the tasks per NUMA node. And the thread depth. And then there's a function display affinity as well. On AMD systems or on Xeon systems, you can use on both of those the NUMA control. So all cores on a node share memory, but all cores on a node do not necessarily share equal access to the memory. The cores on a socket share the L3 cache. Again, that's not quite true. It's cores on a die share the L3 cache. And extra threads can help. Now, we want to find out that task and OpenMP thread affinity. Here's some source code of how we would do this in C. We can actually go through, and there are these intrinsics to find out the mask of whereabouts you are allowed to go on a particular node. Now, if you run this on a standard a standard node, a Linux node, it will return back a CPU set mask that will tell you can run anywhere because you've not actually pinned yourself. You can then go in and set affinity, or so the analogous routine to get affinity is set affinity, and actually start to pin yourself down further on those nodes. That's what these affinity setting mechanisms in app run or by your compiler are actually doing. So if we run one of these codes and see what happens when we run with 4 threads, a depth of 4 on 4 nodes, then it gives this setup core affinity. It's just giving out 0, 1, 2, and 3 as the cores. If we say we want to run a little more, this is a little more complicated. We're running 4 MPI processors and 4 OpenMP threads, and we want to run 2 processors per node, 1 per NUMA node. We get a different output. The core affinity is now spreading over 2 NUMA nodes. You'll see the numbers that are actually output here are 0, 1, 2, 3, and then it jumps over to the next NUMA node, 6, 7, 8, 9. And this one then gets a little more complex still. We're now putting 6 threads on with, we've limited it to 1 NUMA node per node. But this is the sort of output, you can get this code and run these quite simply. And then 1 task per NUMA socket with 2 per node. The same thing could be done on the Rosa machine. So this example, very simple, MPI in it, and then just display the affinity, gives you this output. The impact of the mappings on multi-socket, multi-core systems. If you do an effective mapping, you can also, by looking at that affinity, you can also improve performance, even with these benchmarks that we saw earlier, the NAS parallel benchmarks. You can see by doing the effective mapping, we reduce by a matter of a few percent the performance, the runtime improves. And it tends to get better the more threads you're putting on these things. That's where the sensitivity tends to come into play. With a Xeon type system, instead you have to consider also the hyper-threading aspects of when you're mapping onto these machines. So with and without hyper-threading, if you just ask for a certain number of threads, it may map you onto the same physical core. So you have to be clear that you're actually getting a different physical core if you're not going to fill up all the threads on a node. In this particular case, things slow down almost twice if you're running on the same cores. Because what we're actually doing is OpenMP1, OpenMP2 onto the same physical core would cause a problem. If you get them to go onto separate physical cores, then you get a speed up. But if you go on a 12 core system with 24 threads, if you go beyond 12 threads that are mapped on every other virtual core, then you will start to get a slowdown. You'll get an immediate hit because 2 of them have to share the same core. Okay.
So do I get it right? If you really run only 1 thread on one of these hyper-threading cores, then it is not really hyper-threading anymore, but running at full speed.
Yeah. Speed? Yes, the hyper-threading, exactly. The hyper-threading is, so there's software threading and hardware threading. And this is a way of trying to speed things up with hardware threading. Software threads have been around for quite a long time, and in order to get a thread or a forked process or whatever running on the same process, on the desktop, on the laptop, what happens is you allow one thread to run for a while, then you come in, the operating system will get in the way and it will say, I need to switch around to the other person, to the other process. What it then has to do is it takes a record of all the registers, it takes a record of the program counter, the stack pointer, takes all that, puts it into memory, takes the other processor's information, puts it back into where it was, and then continues. And that's quite a heavyweight thing to do. That's a context switch, and you want to limit those as much as possible, so that the operating system getting in the way causes an issue, as Roberto showed on some slides to do with OS jitter, as we call it, and how Cray had done things with Linux to make it so it was much more uniform. That is to do with how frequently things get in the way, because the operating system itself has to come in and do a context switch to get in the way. The idea of this hardware threading is simply that instead of doing things, for example, on 2 threads, instead of having to do the full switch out, what it does is it says, well, I'm going to have 2 copies of everything at the register level. So it therefore says, well, now I switch in a second thread, okay, I'll give it these registers over here. It can now work on those, so when it does to do a context switch back, it doesn't have to do any of the dumping to memory. If it's only trying to switch between 2 threads, it just goes straight back to the other thread. You'll still get some software threading on top of this that the operating system wants to do, but from a hardware point of view, it can switch between now 2 completely independent tasks in one cycle. And some people have generated this to 4 threads, 8 threads, and so on.
Right, so it doesn't hurt if you have your application running now on a single thread, and the operating system has all other kinds of processes, of course, running as well. It's not that one of the hardware threads is then reserved for some of the operating system tasks, so that effectively you only get half of the speed of that core. It's not like this, as far as I understand it.
Right, it shouldn't be. I mean, the operating system or anything else running on there in a HPC environment shouldn't be very much. It shouldn't get in the way. And if you...
No, even on the laptop or
Right,
PC.
yeah. So yes, it should, and particularly also it depends on what priority it gives your process. So if the nice level is high, then it may be that it's never trying to get you out of the way. It will always try and get something else out of the way.
There will never be disadvantage of hardware threading compared to software threading.
Right.
Never.
Yeah, that's correct. The other advantage that you can get out of this as well, though, why people in some areas of HPC use this, is that if you've got resources that one thread doesn't really want to use, and it's stalling on a particular type of resource, but you have a different thread that's got a different set of resources it wants to use and it doesn't want to share them, then you can get the speed up because it can be switching between the two things and keeping the resources busy. Now, so this is a little interlude away from what we were supposed to be talking about, but for example, we had an IBM Power 5 machine here, which you're familiar with, and we tested this. This had this hardware threading, symmetric multi-threading. We had a set of applications that were basically bounded by linear algebra, dense linear algebra. We had another set of applications that had if branching statements in there, and where any individual two MPI processes would at any point in time probably be doing something slightly different. The ones that were bounded by dense linear algebra, if we tried to run the hyperthreading with MPI-only applications, things were slower, because rather than running 16 MPI processes, we'd run 32. There were no free resources for them to get hold of. You were further along the MPI scaling curve, so things slowed down. So it was a distinct disadvantage. For some of the other applications where they were not sharing the same resource, 2 MPI processes with 2 hardware threads on the same core, we got to speed up. Could be up to 20-25% in some cases. But since most of our workload was the dense linear algebra stuff, we didn't bother using that. That's the other advantage you can get from the hardware threading. AMD are not implementing this. Instead, they're going to, on their next generation processor, have 2 cores that share the resources. So rather than having to switch to allow the thread to go through some separate execution units, 2 sets of execution units, 2 threads will be going at the same time, and then they will just compete for whatever they need at a particular time, rather than actually only one set of instructions being issued. Okay, that's just a design decision of the 2 companies. So you may get some benefit from hyperthreading by throwing more processors or more threads at it if you have some resources within your application that don't share, that aren't competing. And this has been seen as 2 examples. People who do classical molecular dynamics applications where they may have different numbers of neighbors, etc. They may be doing things slightly differently at different times. The other example which showed up was in parts of climate and weather applications where there were aspects of cloud physics, etc., where there were a lot of if statements. And again, it means that different threads are likely to be doing different things at different times. So, performance measurement and analysis, we have a set of tools available for hybrid applications. CRAPAT is the best one from our recommendation on the Cray systems, simply because we're used to it. And 3 minutes over. Yeah. 3. We also have Scholastica, as you were going to say? Yeah, Scholastica should also be on this slide. You know how to use CRAPAT. Key considerations when programming these things. your OpenMP version, as I said, should try to retain those microprocessor optimizations and check those compiler listings. The SSE instructions are very important to make sure it's vectorizing. On a Cray compiler, it will have the capital V, it's vectorizing. If it does instead a capital A, it's done a pattern match. That's better. But don't expect it to pattern match too much. You want to see V's, vectorizations. The listing will tell you if it couldn't do it for some reason. You want to keep the same loop level optimizations and inlining into procedural analysis wherever possible. So your single threaded version shouldn't be considerably slower than your serial version. As we saw, if you get rid of a pattern matching, that will be the case though. Just to reiterate main advantages of using OpenMP, you know why you want to use OpenMP, I presume. And just to say the myths and realities of this, people who say OpenMP is mostly or always slow, that isn't the case. It can be faster. And we've seen examples where an MPI and OpenMP on a small scale can be faster. I would personally say, from having read several papers and from experience, that shouldn't necessarily be the reason you actually go in for this in the first place. Most people, they're interested in pushing out the scaling limits to get a faster time to solution on more cores. Or one of these other considerations to do with memory, etc. But trying to just speed your application up on the same number of processes where MPI is doing a good job it may be worth doing, but it may be a bit of wasted effort. Another example, OpenMP adds a lot of overhead. Well, you could get a lot of overhead if you're doing a lot of switching in and out of threads, if there's a lot of closing down of loops and all the rest of it, but typically that isn't the case. OpenMP doesn't scale. It should scale reasonably well if you parallelize most of your application on a NUMA node. If you start going beyond NUMA nodes, you may get some scaling issues. And MPI threaded versions are slow. Well, in this particular case, Sadaf tested actually all those different things, thread single, thread funneled, and thread multiple. She didn't find, on a few examples, any particular problem with using any of them with different MPI init thread variants. But I would still say if you can get away with a simple version like MPI thread funneled, then please do. Because just because a few tests for simple cases don't show anything up, doesn't mean that something bad won't happen later. Just to mention as well the future of MPI and OpenMP as we go forward, to take account of the threaded model. This is the current design. Even if you're on two application threads sharing a process, would share the same MPI interface, but a separate one on the same node wouldn't. In the future, they're now trying to find things so that there can be a lot more sharing on a node of memory, so memory allocation that both processes can see to speed things up. The directive-based programming, just want to reiterate, there is a course here coming up at the end of March for people interested in GPU programming using PGI accelerated directives. March the 29th, 31st, just go to the website, register if you're interested. Cray are following a similar pattern, and both of these companies are involved in trying to get these accelerated directives into OpenMP. So anything you do now with OpenMP is not wasted effort when you move forward in the future, hopefully, to GPUs. And here is a set of references to tutorials and etc. And as we said before, if you really want some examples of OpenMP, the best place to go is to grab hold of the actual OpenMP document itself, the standard. It's mainly examples and only a little bit of standard.